Hello everyone, welcome back to ECE 161. This is part 2 of Lecture 10. Lecture 10 is about fast Fourier transform. Again, this is Tolentino, your instructor for today. So, from the previous video, we've discussed the first step in making the DFT computation more efficient, which we call the divide and conquer approach. Okay, but we've also noted that we have not yet reduced the computational complexity that much um, much larger because we only reduced it by a factor of 2. Can we further reduce it by some number by decomposing, right, 500 into a smaller number? Okay, so just a review, capital N, when capital N is a prime number, we are still able to um, this approach because we can always do zero padding, right? Zero padding again does not include additional information to the signal, right? But somehow, in some cases, it is useful to do zero pad because it is more convenient to do DFT when it is of a certain length. So in this case, uh, we want to um, we want the length of the signal to be some number for us to be able to use this approach, specifically the radix to FFT algorithm. So we want it to be a power of 2. Okay, so if for example n is 1000, okay, we cannot use this, but we can use this algorithm when we pad 24 zeros to that signal. Okay, which is not, it's not entirely bad to do that because you're just padding numbers or zero numbers, which is okay. Now, again, n is r to the v, where r is our radix. So in this case, radix 2, therefore r is 2. So n is 2 to the v. N is 2 to the v. So again, radix to FFT is the more common. So we will be discussing this. And the other radixes, for example, radix 4, we will understand it when you understand radix 2. So we will just discuss it in this video. And if you want to understand other approaches, you can always consult the book. Okay? But the important is we understand radix 2. Okay, now, for the n is 2 to the v point DFT, the first stage is selecting m is n over 2. Okay. So again, m is the columns, right? L is 2. Okay. So we have 2 rows here. Okay. So now, we are computing 2 m-point DFTs. Okay. Where the first signal, F1, is corresponding to the even numbered samples. Okay. Because right, x0, x1, x2, x3, dot 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 until we reach capital M is n over 2. Okay. This one is our f1 of n, the whole signal here. Okay. f2 of n corresponds to our odd numbered samples. Okay. So n is from 0 to, what is n over 2? M minus 1. Okay. So 1000, for example, 1024, M is 512. Okay. Is that right? Okay. So if we do that, okay, take a look at this first. This is our original DFT, right? Okay. Now we decompose this DFT into two summations. So the first summation is from 0 to n over 2 minus 1. This is for f1 of m. Okay? This is for f2 of m. Wn, n is equal to 2m here, right? So the mapping a while ago is correct? Right, n is 2m. And the other one is n is equal to 2m plus 1. K remains the same. So we have 2mkn. K times 2m plus 1. Okay, now, this relationship will now come into play, okay? So, what is this relationship? This is still periodicity, right? No, sorry. Diba recall that we've done this before, right? When we have squared here, we can always bring it down here. So we have Wn over 2. Okay? So when we do that, we have here 2mk. We bring down 2 here, resulting to Wn over 2 mk. Okay? On the other hand, we have here, we bring down this 2. Okay? So n over 2 km, but we have extra term here, wk. Okay, so we bring it here. Okay, now this 2, okay, is the m point DFT. M point DFT of f1 of m. Right? This one is also the DFT, m point DFT of f2. Right? Because n over 2 is m. Right? So, this is equal to capital F and this is equal to capital F. So, we have this equation. The DFT of the whole expression is equal to the summation of two terms. The first one is the m point DFT of the even numbered samples, and the second term is the m point DFT of the odd numbered samples multiplied by this Twiddle factor. Okay. Now, another thing is we are now exploiting this relationship. Okay, since f1k and f2k are periodic over n over 2 samples, okay, so that means f1 of k here is the same as f1 of k here, f2 of k here is the same as f2 of k here, and we are now exploiting this. This one is symmetry conditions, symmetry property. Okay, so from W and K, so if x of k is at k plus n over 2, this is also W k plus n over 2, right? Over n, which is equal to negative W n k, which is just this one. Okay? Now, why do we do that? Okay. So this is equivalent to the following flow graph. Okay? Where the first term is what do you call this? F1 of k. This is F1 of k. And This is add. Okay, sorry. Um, again. This is f1 of k. This is f2 of k. We multiply f2 of k by wn. So we have here, when we add them up together, we have here x of k as f1 plus wn f2. On the other hand, xk plus n over 2 is equal to f1k. This is f1k, right? f1k plus negative f2k. f2, is this correct? f2k wn. So f1k minus wn f2k. So this flow graph is actually very convenient sometimes. So it's just a graphical representation of these equations. So this is also called the butterfly, because I don't know if you see it, but they said that it resembles a butterfly. Okay. This is the very important application here. So if we do this one, we have here f, what do you call this? We have here f1 and f2 as 512 point DFTs, right? 512 samples, right? We can still further decimate it. So if we decimate f1, we will be getting 256. f2, we will be getting 256 samples, and then f2 256. So we have 4 and 256. 256 samples until we decimate it until f1 and f2, or all the following f's will be m is equal to 2. So to further demonstrate it, I'll start here from what I've discussed. Okay, so what's this? It's hard to but basically, we have here two f, right? f1 of n and f2 of n. We get their 2-point DFTs. Okay, but we further decimate it until we get this one. Okay, so for example, n is equal, this is just first stage. N is equal to 8, first stage. Okay, if we have n is equal to 8, we have 3 stages for our FFT. Okay, the first stage is decimate until we have 4, until you have 4 samples. Okay, and then you decimate those 4 samples, you have 2. Okay, and then the third is, I think you get the picture already. Okay, but basically that's how you do FFT. You further decimate it until you come up with m is equal to 2. Okay, so this one is the butterfly effect, right? So the first stage will be, this is again n is equal to 8. Okay. Okay, this is xk, and then this is xk plus n over 2. Okay, take note of the indexing. Okay, x0 maps to x0, x4 maps to x1, x2 maps to x2, so on and so forth. Okay, so this is what we call as the bit reversed indexing or addressing. Because, for example, let's take for example 4. The bit representation of 4 is 100, right? 4. And then the bit representation of 1 is 0, 0, 1. On the other hand, the bit representation of 6 is 1, 1, 0. The bit representation, the mapping here is from 6 to 3. The bit representation of 3 is 0, 1, 1. Okay, so what's happening here? Okay, um, I know that is we do not have um, in the digital signal processor side. This is a very important representation. Okay, because you just have to change. You already have a certain representation for this one and then for this one. So this is an important principle so that we are able to do addressing of both the time domain and the frequency domain. Eh, we have a representation already, which is the bit reverse representation or addressing. So this is an important principle. Now, this one is decimation in time. Okay, the other version is decimation in frequency. Because decimation in time, because you are decimating the time domain signal into two two subdivisions. Okay, so as we've recalled, from x of n, we have f1 of n and f2 of n. We decimate time into two. The other one is we decimate frequency into two. So we have x of k. So you could notice here, right, x of the indexing for frequency is different. Okay, so sometimes it is uh, because it has something to do with the shuffling, right? So sometimes it is more convenient for us if we decimate in frequency. Okay, because in this case, only the frequency indices are shuffled. Okay, so frequency x0, x4, x2, x6, right? But then we could show that it is still bit reversed. Okay, so 4, 1, 6, 3, etc., etc. So it's up to you, or it's up to the designer if they want decimation in frequency or decimation in time. But it is still the same approach. Okay, we utilize this butterfly effect or butterfly flow graph. Okay, so now we discuss why is this more efficient. Okay, so again, fast Fourier transform. This is just one algorithm, the radix 2, but there are other approaches, like the radix 4, split radix. So now, why is the FFT more efficient? It requires capital N over 2 log base 2 of N. So for example, N is 1024. So what is N over 2 log base 2 of N? Okay. N over 2 is 512 multiplied by what is log base 2 of this number? 10, right? So 5,120. Is this correct? I hope this is correct. No? So from the original is n squared, right? 10 to the 6. We now have this improvement factor. Okay? This, ito pala yun. This one. From this, we have 5,120. Divide this one by this. We now have 204.8 improvement factor. So, if we have, for example, it takes us 60 minutes or 1 hour to compute this using the direct approach. If we have this kind of factor, we now have 60 divided by 200, some seconds only of computation. Okay, so it really saves up save us up a lot of time. Okay? So actually, as I've said, this scales up to the length of n. So if n is 8, then it's okay. It's okay to use DFT because DFT is more, what would I say? DFT is compute, it is more doable by hand, right? We can do it this by hand. Okay? And the improvement factor is just 5. So if it takes us 10 seconds, then FFT just takes us 2 seconds. Okay? But if n increases until 1024, then it is much better to use the FFT. Okay? So in summary, okay, we can reduce the computational complexity of DFT by decomposing into smaller DFTs. Okay, we've shown it a while ago. The most common FFT is the radix 2 algorithm, which we've briefly discussed a while ago. The good thing here is that the FFT exploits, diba? Um, uh, WK plus N over 2 is equal to negative WK. We've done that a while ago, right? So it exploits this, and it exploits this property, the periodicity, basically symmetry and periodicity properties, which the direct computation does not exploit. And this is the most important point, is that the speed improvement factor of the FFT increases as the length of n increases. So if you have a very long number or long sequence, then it is much better to use the FFT. Okay? So this will be we will be able to demonstrate this, or we will see this speed improvement factor when we do the DFT in our interactive exercise. So stay tuned with that. But this ends our lecture. So this is our references. This is the main reference that I've used. Okay, so for further reading, you may also check out the book by Mitra on FFT. Okay, so thank you, class. That ends our discussion. That ends lecture 10. And see you on the next lecture.